les impacts directs sur la santé, hein, c'est-à-dire les sources d'exposition et les sources d'absorption. Bon, ça, je voulais vous montrer le tint, mais on fait ce travail-là dans le cadre d'un groupe qui s'appelle the International Team on Nanosafety, qui travaille là-dessus. Pourquoi, dans le cas des nanos, on a aussi peu d'évaluation? C'est que dans le cas des OGM, comme dans le cas des nanos, on est parti au niveau des pouvoirs publics d'une prémisse économique qui s'appelle le GRAS, Generally Recognized as Safe. Autrement dit, ce sont des produits suffisamment différents pour être profités, mais pas suffisamment différents pour faire l'objet d'une évaluation rigoureuse et systématique. C'est pour le moins sérieux. Il y a la France qui, depuis le mois de février dernier, a mis en place un dispositif permettant de savoir au moins ce qu'il y a sur son territoire. Mais c'est le seul pays au monde, pour l'instant, qui a ça. Donc, il y a une insuffisance, une opacité de l'information et de la recherche, une absence de définition claire des catégories, une absence d'étiquetage, une absence de données fiables et indépendantes, un décalage absolument hallucinant entre la recherche et l'évaluation et l'encadrement. Et je n'ai pas résisté à vous montrer comment ça se construit tout ça. C'était une présentation qui a été faite à la Commission européenne et c'était tout à fait intéressant. On dit, qu'est-ce qu'il faut pour développer ce champ-là? Alors, il faut vraiment supporter le développement et avoir une gouvernance responsable, mais certaines conditions pour le développement doivent être en place. Il faut que les barrières pour la croissance du commerce soient identifiées et enlevées. Il faut... et quand on regarde tout ça, on se dit, mais c'est quand même pas sérieux. Et parmi les barrières qu'on identifie, c'est les coûts, par exemple, des tests environnementaux pour la santé, pour l'analyse du cycle de vie. Donc, c'est quand même rassurant de voir que les gens qui s'occupent du développement de ces technologies du côté des pouvoirs publics peuvent avoir des perspectives comme celle-là. Merci de votre attention.
Sustainability and energy efficiency are concepts that have gained great importance over the last 2 decades. An efficient use of all resources is society's today demand now. Buildings account for up to 60% of the world's energy consumption and also for the highest potential for energy savings. Sustainability with regards to buildings starts from the site selection stage and continues even after building occupancy. The roof is a key element of the building envelope, whose potential has been explored to a very limited extent. Roof construction has come a long way from simple rocks and clay tiles to present-day polymer and smog-absorbing tiles. Roof should be designed for longevity, performance, and high insulation. In order to take the best out of any building envelope element, it is necessary to integrate it to its surroundings. Design it in such a fashion that, while providing necessary protection against the exterior environment, it utilizes the environmental factors to the advantage of the building's performance. At near ground levels in cities, due to the presence of various obstructions such as vegetation, building, etc., wind speeds are generally low. As we go higher in the atmosphere, there are fewer obstructions to the wind flow and hence higher flow speeds that cause high pressure or suction that could potentially cause damage to building, cladding both on the facade as well as roofs. So, as we build higher construction, winds becomes an important factor to be considered. Some of the wind flow phenomena that induce high suctions are the following. First, the flow separation and reattachment. When objects with sharp corners, such as buildings, are exposed to the path of wind, the flow accelerates around the corners and edges, thereby inducing high suction on to the surfaces. Second, the downwashing effect. This type of flow occurs when buildings of considerably different heights are located close to each other, or in the case of podiums of tall towers. Wind is intercepted by the taller structure and washed downwards onto the roofs of the shorter structures. And third, the wind channeling or venturi effect. Buildings situated side by side cause wind to channel and accelerate in the small gap between them, thereby inducing high suction on the leeward building's edges and uncomfortable wind environment in the channel. Photovoltaic system, or PV system, are used to convert sunlight into electricity. They are safe, reliable, low-maintenance source of solar electricity that produces no on-site pollution or emissions. PV systems incur few operating costs and are easy to install on most houses. Unglazed transparent collector, UTC, are ventilation air preheaters that preheat air as it drawn into the buildings. UTCs, like PV systems, are easy to install and provide for an effective redirection of solar heat toward air and water heating purposes. Usually free of obstructions with good exposure to the sun, rooftop solar installation represent an efficient use of space. UTCs has found their place in space heating, pool heating, and crop drying application. Performance of thermal collectors in general depends largely on the heat absorbed by the absorber plate. Exterior convention heat transfer coefficients for building surfaces are normally determined experimentally because of their dependence on a variety of parameters like the building geometry, wind speed and direction, local topography, turbulence intensity, etc. Ongoing research at Concordia University examined the effect of wind velocity, direction, and distribution over large areas of solar thermal and building integrated PV thermal devices. The studies are being continued to assess and quantify the effect that wind has on the complete performance efficiency of the devices. With global demands for sustainable development, manufacturers, researchers, and designers are working hard to protect the environment. Sustainable roofs could be defined as roofs that use efficiently energy throughout their life cycle and benefit the environment through energy conservation, either with the aid of photovoltaic panels, wind turbines, or vegetation. The use of green roofs in buildings during the recent years has shown almost a 50% improvement in energy conservation. Green roofs are alternatives contributing to higher sustainability of resources and energy conservation as well. There are no limitations in design and individuality. Green roofs are beneficiary because of their many advantages. Reduce life cycle costs, improve air quality, ambient temperature reduction, stormwater management credit, sustainability and preservation of the environment, reduce loads of sewage systems by gathering large amounts of rainwater, protection of the main roof from UV radiation and temperature fluctuations, and reduce noise transfer. Energy efficiency gains provided by green roofs appear primarily during the summer months, as the passive cooling effect caused by them is at least 3 times bigger. Usually, dark roof surfaces have fluctuating temperatures that vary with ambient air temperature and intensities of solar radiation. On the other hand, green roofs are able to regulate the temperature changes and consequently modify the heating and cooling needs of the entire building. It occurs very often in countries with heavy snow falling during the winter that snow accumulates in the roof of a building. Because of its properties, snow unquestionably affect the heat transfer between the outside and the inside of the building through the roof. Also, because of the wind gusts on top of the roofs, we observe the phenomenon of snow drifting and accumulating in different areas of the roof. It is known that using vegetation on a green roof helps moderate wind erosion of the soil on them. The more the soil is covered with plants, less is the erosion produced by wind. This happens because the rooting system of the plants that are specifically used for this cause in green roof is strong enough to hold the soil at its position even during high wind phenomena. Protection from the wind is also given with the addition of erosion blankets and other erosion control techniques. In order to control uplift, soil particles are strengthened with the incorporation of geotextile materials like lightweight expanded clay. Snow accumulation on roof-mounted solar collectors is a very important topic of research and is very important especially on high latitudes. The effect of this phenomenon on the panels are a very low or no power generation. Peak power outputs may be reduced by up to 50% by snow cover of 75 to 80% on PV area. Yearly losses can range from 0.3 to 2.7%. Third, self-cleaning depends on inclination, angle, and ambient temperature. Urban areas are generally warmer than surrounding rural, less developed areas. This phenomenon is commonly known as urban heat island effect. Urban development consists of a mix of high and low buildings, and the aerodynamic configurations associated with rectangular buildings of varying heights cause accelerated flows at lower levels. This increase in wind speeds may be uncomfortable or even in some cases dangerous. This in turn affects the commercial success of buildings. Several wind comfort criteria and comfort scales, like the Beaufort scales, are available in literature, based on acceptable wind speeds for human activities and percentage exceedance of wind speeds above acceptable limits. Wind comfort is particularly important in the case of areas meant for long-term occupant use at a roof level, such as terrace. If conditions in an area do not meet the acceptable comfort criteria corresponding to the intended occupant activity, chances are that there will either be complaints of nuisance by the users or that the area might not be used for its intended purposes. Wind tunnel testing is the most robust method to estimate the flow patterns around buildings. By using scale models of existing and or proposed buildings and its surrounding, flow patterns, area of discomfort, and possible safety risk can be assessed accurately. Natural ventilation is almost always linked only to building fenestration. Developments in this subject have brought about ways to naturally ventilate buildings. Here is a brief review of one such innovation in this area: the venturi-shaped roofs, also called ventec. The specific shape of the roof is intended to drive natural ventilation by forcing wind to channel through roof construction into a vertical channel in the center of the building. This flow is directed through shafts and ducts into the building for ventilation. A case-by-case evaluation of wind flow around buildings will be necessary in the future, in some cases to provide answers to the various aspects described in this presentation, which in summary are: how is the performance of the green roof affected by wind in high-rise and low-rise buildings? What should be the standards for the optimal design required to achieve adequate structural performance and sustainability under wind loads? In which part of the roof should we develop green roofs based on snow drifting predictions? How is the performance of photovoltaic arrays affected by wind on a roof? And what is the optimal positioning on each roof for maximum performance? And finally, how can passive ventilation, heating, or cooling strategy be incorporated into the architecture of a building based on its specific surroundings?